Hello everyone and welcome to this new video. Today we're going to talk about the Gudermannian function, which is a very interesting function, especially from a historical perspective other than from a mathematical perspective. In fact, not only, it's important for mathematics, we will see later why, but it also has a very interesting relationship with the Mercator projection, which is perhaps one of the most famous projections out there. So let's start by defining the Gudermannian function. The Gudermannian function is commonly defined as GD of psi or psi's and hyperbolic angles, defined as the integral from 0 to psi of the hyperbolic secant of t dt. So mathematically, the Gudermannian function provides relates areas of circular sectors to areas of hyperbolic sectors. So let us now visualize the Gudermannian function, and before we actually introduce its relation to the Mercator projection, let's actually see mathematically what does it do. So let's draw a pair of axes, x and y. And let's draw a circle of radius 1. So we're all accustomed to the parametrization of this circle, which is just given by cos phi, sin phi, with phi being between 0 and 2 pi. So now let's fix a point on this circle, which we will call n, big N. And let's take whatever point on the circle that we will write as cosine phi sin phi. So now let's also consider in our xy plane a hyperbola, which I'm going to draw in blue. So a hyperbola given by the equation x squared minus y squared is equal to 1. So now let's consider the line that passes between n and this point here, cos phi, sin phi. And let's actually consider the point on this line, the intersection of this line, which is uniquely determined, of course, with this hyperbola. So it turns out it's actually a point P. And this point P is we know that the hyperbola can be parametrized with the hyperbolic cosine and hyperbolic sine function. This point we will call it cos psi sinh psi. So it turns out that our phi, so our trigonometric circular angle phi, and our hyperbolic angle psi, that we find basically by considering this kind of this relationship between these curves in a stereographical projection fashion, they're actually related by this function. They're related by the Gudermannian function. In particular, our phi, or trigonometric angle phi, is the Gudermannian of psi, of this hyperbolic angle, and psi is the anti-Gudermannian of phi. We will later see, the anti-Gudermannian is just the inverse function, but we will actually have to be careful with the domain of this function, and we will see why later. So this is, geometrically speaking, what the Gudermannian does and why the Gudermannian mathematically is important. So it's basically a mathematical bridge between trigonometric angles and hyperbolic angles. However, this is not the only reason why the Gudermannian function is of interest. So as I mentioned before, I'm sure some of you are accustomed with the Mercator projection. The Mercator projection is a cylindrical conformal projection of the globe. However, even though the projection preserves angles as a consequence of the theorema egregium by Gauss, we know that, of course, the surface of the Earth that we can model as a manifold, as a two-sphere, cannot be represented on a plane without distortion. So while the Mercator projection preserves angles and thus directions, it doesn't preserve areas. In fact, we all seen the maps of the Earth, probably the Mercator projection, where Greenland is huge and it's almost as big as Africa, but it's actually way smaller. In the same way, Alaska and Australia, Alaska seems way bigger than it actually is, and in the same way, Madagascar seems way smaller. So we have these problems with the map, but they're actually intrinsical to the geometry of the objects we're dealing with. So the conformality of the Mercator projection, actually from it and other considerations, we can derive the formulas for the x and y coordinates on the projection in function of the latitude and longitude that we will denote by lambda and phi. In fact, we will get that the x coordinate on the projection is r times l minus lambda naught, and y is r, the natural logarithm of the tangent of pi over 4 plus phi over 2. Where here, as I said earlier, lambda and phi denote the latitude and longitude, and r is the radius of the globe. Both of these follow from the isotropy of scale factors, which is a corollary of the conformality of the Mercator projection. And from this expression, and actually we can derive the inverse expression for the longitude and latitude, lambda given by lambda naught plus x over r, phi is given by 2 times the arctangent of e to the y over r minus pi over 2. And so here we actually see the connection between the Mercator projection and the Gudermannian, because it turns out that this expression right here for the y coordinate on the projection is actually the r times the inverse Gudermannian of phi. And it turns out that the expression for the latitude, phi, is actually the Gudermannian of y over r. We will prove these identities later in the video that I outlined now, and we will see that they follow pretty quickly from the integral definition that we gave above. So as we saw now, we gave a little bit of motivation of why the Gudermannian function would be interesting to study. And before we actually dive into proving some facts about it, let's actually finish by talking about a little bit of a notational aspect. And so, why do we denote the Gudermannian function as GD, and why do we call it the Gudermannian function? The name actually comes from the mathematician Christoph Gudermann, which was a mathematician active, Christoph Gudermann, active in the 19th century. However, the function was actually introduced by Lambert in the 18th century. The relation of Lambert to the work on the Gudermannian function is actually preserved by some notation that we still adopt nowadays. For example, the inverse Gudermannian function, which is the GT to the minus 1 of phi, is actually sometimes denoted as lam of phi, or the Lambertian of phi. This said, let's actually prove the first identity, and we're going to highlight it. I'm going to say proposition. I'm going to say that, we're going to claim that the Gudermannian function psi, or the Gudermannian function of psi, is equal to 2 times the arctangent of e to the psi minus pi over 2, which would actually prove what we set up here to be true. So let's actually give a proof of this. This is rather straightforward. So the Gudermannian of psi is the integral from 0, so the integral from 0 to psi of the secant of t dt. But the secant of t is of course 1 over the hyperbolic cosine cosh of t, and cosh of t is e to the t plus e to the minus t over 2. Keeping this in mind, we can write all of this as this integral. We can write this integral as integral from 0 to psi of 2 dt over e to the t plus e to the minus t. So now we can multiply and divide by e to the t, yielding above 2 times e to the t. And below, e to the 2t plus 1, all dt. And now, this is actually, this is actually a very easy substitution. We can just substitute u to be e to the t, and well, du will just be e to the t dt, and this becomes the integral from 1 to e to the psi of 2 du over u squared plus 1. And well, the integral of 1 over u squared plus 1 is just the arctangent. So we have 2 times the arctangent of u, with u going from 1 to e to the psi. And well, this is actually just the arctangent of e to the psi, all minus pi over 4, because we know the arctangent of minus pi over 4, but actually distributing the 2 over this expression yields 2 times the arctangent of e to the psi minus pi over 2. And this is our desired expression for our Gudermannian function. So this proved the relation that we used earlier to show the relationship between the Gudermannian function and the molecular projection. Another interesting identity about the Gudermannian function is the following, and we're gonna write it down here because the space is finishing. So fact number 2, and that is that the Gudermannian function of psi is equal to the arctangent of the hyperbolic sine of psi. Let's highlight this result so we don't mix it up with the proof. And so now we're going to actually prove it. So we start again by the definition of Gudermannian, which is just the integral from 0 to psi of the hyperbolic secant of t dt. And now what we do is we recall again that, of course, the hyperbolic secant is 1 over the hyperbolic cosine of t. We multiply by hyperbolic cosine of cos t over cos t, which is just 1, and we get cos t over cos squared t dt. But remembering the identity cos squared t minus sine squared t is equal to 1, we can substitute 1 plus hyperbolic sine of t in place of hyperbolic cosine squared of t. So I'm going to do that. And now by performing a substitution, namely u is equal to hyperbolic sine of t, we're gonna get the following integral. The integral from, well, the hyperbolic sine of 0 is 0, the hyperbolic sine of psi is sinh psi, and here we're gonna get, well, the derivative of sin t is cos t, so we're gonna get that du is cos t dt, and so we're gonna just get du 1 plus u squared. This is just the the arctangent of u evaluated between 0 and sinh of psi, and this just reduces to the arctangent of sinh of psi, and this completes the proof of this fact. And from this we can actually, by just applying the tangent to both sides, we get that the tangent of the Gudermannian of psi is equal to the hyperbolic sine of psi, where of course psi is our hyperbolic angle. So what does this mean geometrically? Let's try to interpret this result. And well, if we draw our pair of axes, x and y, and we draw a circle, let's draw it red, just to distinguish between the two, and then we're going to draw our hyperbola. I'm going to draw just one sheet because it's safe space. And well, we have that GD of psi is actually our trigonometric angle as a function of our hyperbolic angle. So let's say that this is a point on the circumference. This is our phi in radians. This is cos phi, sin phi. This is our point here. So what this identity is actually saying is that the tangent of this point, which is gonna just be this value right here, that I Actually, let's change color. So this value right here, tangent of phi. Well, what this is saying is that the tangent, so this height here, is equal precisely to the height of the point, the corresponding point on our hyperbola, because this is equal to sinh of psi, which is this value here. So this is the geometrical meaning of this identity. This identity is actually the mathematical relation that relates via the Gudermannian the hyperbolic angles and the circular angles, the trigonometrical. So hyperbolic trigonometry and circular trigonometry. One could also see a more physical interpretation of this identity, namely one that would relate circular rotations, so rotations represented by the matrix cos theta minus sine theta cos theta, that I'm sure most of you are familiar with, maybe from a course in linear algebra, to hyperbolic rotation. These actually turn out to be elements of the Lie group U1, that is also known as the circle group. And well, if the viewer is not comfortable with the notion of Lie group, then just or just referring to the complex numbers of norm 1. Well, because this is actually the matrix representation of complex numbers. In fact, we know that complex numbers can be used to represent rotations. So we can actually write this also as e to the I theta. And this also actually opens another window of visualization and interpretation of this identity. Not only this represents a bridge between circular rotations, and well, as we said earlier, physically, hyperbolic rotations are deeply related to Lorentz transformations, but also these potentially relate unitary complex numbers. In fact, this is U1, as we said earlier, so the group of complex numbers of norm 1, and unitary split complex numbers. So we could say, and again, split complex numbers, so let's say C to Rj. And well, split complex numbers are nothing but an hyperbolic version of complex numbers that can be written in the form x plus yj, where j squared is equal to minus 1 instead of 1. And this actually turns out to be another algebra over the reals, two-dimensional algebra over the reals, which is not isomorphic to the complex numbers. But here the word isomorphic, in case the viewer is not familiar with it, can just be replaced by algebraically the same. So we basically, this is just an algebra which is not algebraically the same as the complex numbers. That is two-dimensional, and again, two-dimensional here refers, of course, to the underlying vector space, but can be reduced, of course, to the intuitive concept visually, to the notion of dimension visually. So this is not the only interesting identity relating hyperbolic angles and circular angles that we will explore, but there are many other identities that are rather interesting. In particular, let's prove the following. And what we will claim is that the tangent of 1/2 the Gudermannian of psi is equal to the hyperbolic tangent of 1/2 psi. So this is another interesting identity, and let us actually prove it. So this again follows from the integral definition of the Gudermannian. So we know the Gudermannian again is the hyperbolic secant t dt, the integral from 0 to psi of the hyperbolic secant t dt, that can be written as dt over cos t. Well, now recalling the identity, cos t is equal to 1 plus the hyperbolic tangent squared of t halves over 1 minus the hyperbolic tangent squared of t over 2. And using a substitution, so we're gonna first write all of this as the integral from 0 to psi of, well, the reciprocal of this, which is just 1 minus the square tangent over 2, 1 plus square hyperbolic tangent of t over 2 dt. And now we're gonna perform a substitution, namely we're gonna set v equal to the hyperbolic tangent of t over 2. From this we will get that dv will be equal to 1/2 secant squared of t halves dt. And substituting all of this by also being careful in changing the bounds of integration will yield the integral from 0 to the hyperbolic tangent of psi over 2, 1 minus v squared over 1 plus v squared, all times, well, dt will just be 2 times 1 over secant squared t halves. So this will be 2 dv over, well, secant squared of t halves is actually just 1 minus tangent, hyperbolic tangent squared of t halves. So this will just be 1 minus v squared. Now the 1 minus v squared and 1 minus v squared will cancel out, and this will give the integral. And well, by the linearity of the integral, we can bring the constant up front. This will be the integral from 0 to the hyperbolic tangent of psi halves of dv1 plus v squared. And what we know what this is just the arctangent of, well, v evaluated from v that goes from 0 to the hyperbolic tangent of psi halves. And this will just reduce to the 2 times arctangent of the hyperbolic tangent of psi halves. And this concludes the proof of our result, and that yields basically the following identity. In fact, what we obtained was that the GD of psi was equal to 2 times the arctangent of the hyperbolic tangent of psi over 2. And by just manipulating the expression, we get that the tangent, by applying first one half to multiplying the first one half to both sides and then applying the tangent of 1/2 GD of psi is equal to the arctangent of psi halves. And this is our result. And also this has, of course, a geometrical intuition that we can visualize as follows. So we have our point here as before, cos phi, sin phi. And well, we know our tangent is just this point here. So half the tangent will be roughly here. So this will be tangent of phi over 2. Because recall that GD of psi, so the Gudermannian of a hyperbolic function, is our circular angle. So yeah, the Gudermannian of our hyperbolic angle is our circular angle, and thus what we get is that this value right here, so the tangent of phi halves, that is roughly here situated geometrically, is equal to the hyperbolic tangent of psi over 2, which is the hyperbolic tangent of our hyperbolic angle. So this is again another very interesting relationship that the Gudermannian function constructs between hyperbolic angles and trigonometric circular angles. But now let's actually look at some other identities that we can derive from the inverse Gudermannian function that we will derive now. In particular, going back to our identity GD of psi is equal to the arctangent of the hyperbolic sine of psi that we have up here, we can derive an expression from the inverse Gudermannian. So let's note our inverse Gudermannian as phi, as before. And by applying the tangent to both sides and then the arc sine, the arc hyperbolic sine, we will get that psi that we will call the inverse Gudermannian of phi, or alternatively the Lambertian of phi. It's actually equal to the arc hyperbolic sine of the tangent of phi. And so this is an expression for our inverse Gudermannian. Well, there's actually an integral representation for our inverse Gudermannian function too that we will derive here, and we'll label this as fact number, well, let's just not label it, and it's the following. It's the inverse Gudermannian of phi is the integral from 0 to phi of secant of t dt. And so this is pretty interesting also analogy to the original function that was the integral of the hyperbolic secant. So let's actually see how we can derive this. So we will start with our identity up here, so this one. So we know that the Gudermannian, so for our proof we will start from the identity that we derived above for the Gudermannian function, that was the Gudermannian function, the Gudermannian of psi, that we will denote for simplicity by phi, is equal to 2 times the arctangent of e to the psi minus pi over 2. So now, by adding pi over 2 to both sides and dividing by 2, what we will get is that phi over 2 plus pi over 4 is equal to the arctangent of e to the psi. And now, by applying the tangent to both sides, we will get that e to the psi is equal to the tangent of phi over 2 plus pi over 4. Now what we will do is we will apply the addition identity, the famous addition identity for the tangent that we will recall up here. That is, the tangent of x plus y is equal to the tangent of x plus the tangent of y all over 1 minus the tangent of x times the tangent of y. And I'll highlight it like so that it's easier to see. And basically what we will get is tangent of phi over 2 plus 1, because the tangent of pi over 4 is just 1, all over 1 minus the tangent of phi over 2. And here we'll use another identity, in particular the half angle identity for the tangent, and by substituting that in here we'll get 1 minus the cosine of phi over 1 plus the cosine of phi plus 1 over 1 minus the cosine of phi, 1 plus the cosine of phi. And now by multiplying all of this times 1 plus the cosine of phi, which is just 1, we will get 1 minus cosine phi plus 1 plus cosine phi over square root times 1 plus the square root of 1 plus cosine of phi minus the square root of 1 minus the cosine of phi. Now by multiplying all of this by 1 minus cosine of phi plus 1 plus cosine of phi, which is again over 1 over itself, so over all this, which is again just 1, we will get that this is equal to 1 minus cosine of phi plus 1 over square root of 1 plus the cosine of phi squared all over 1 plus the cosine of phi minus 1 plus the cosine of phi. And this simplifies to, let's develop the square up, by calculating the square upstairs and rearranging it downstairs. So we get 2 times the cosine of phi, and upstairs we get 1 minus the cosine of phi plus 1 plus cosine of phi, all plus 2 times 1 plus the cosine of phi times 1 minus the cosine of phi. But we notice that we can rewrite this as a difference of squares, in fact by expanding the product under the square root, and so we can rewrite all of this as 1 minus the cosine of square root of phi all over square root. And well, here on the other hand we can cancel the cosine, and we get 2 plus 2 times the square root of 1 minus the cosine squared of phi. But this is precisely a sine squared of phi, and so what we get here is the 2 cancel out. Now this becomes just 1 plus sine phi over cosine phi, which is just secant phi plus tangent of phi. So now what we have is that this is equal to, by the transitivity of equality, to the exponential of psi. So bringing this up here, down. So bringing this down here, this is actually equivalent to saying E of psi is equal to secant of phi plus tangent of phi. And here actually we should be careful and specify that our angle phi is in absolute value less than pi over 2. Because of some of the manipulation that we did earlier with all the square roots. And now by just applying the natural logarithm to both sides, we will get that psi is equal to the natural logarithm of the secant of phi plus tangent of phi. But this is a famous definite integral, namely the integral of from 0 to phi of the secant of t dt. And so we have obtained our identity for the inverse Gudermannian. Let's write it here. So this is our identity. So from the inverse Gudermannian function, many other interesting identities can be found that relate hyperbolic angles and circular angles. For example, remembering that the inverse Gudermannian for the identity that we derived earlier is the inverse Gudermannian of phi is equal to the arc sine to the arc hyperbolic sine, so sinh to the minus 1, or arc sinh of the tangent of phi. We can actually see that the hyperbolic sine of the inverse Gudermannian of phi is equal to tangent of phi. And this is another interesting identity relating hyperbolic and circular angle. But it doesn't stop here, because, for example, many other identities can be found, such as cosine of phi is equal to the hyperbolic secant of psi, or alternatively, the cosine of the Gudermannian of psi is equal to the hyperbolic secant of psi, or, for example, the secant of the Gudermannian of psi is equal to the hyperbolic cosine of psi. And so all of these identities relate together hyperbolic angles and trigonometric angles without the aid of complex numbers. In an alternative way, as the classical identities, complex identities, hyperbolic sine of iz is equal to I times sine z, and cosh of iz is equal to cosine of z. So an alternative way to relate hyperbolic angles and circular angles. So let's conclude this video with a little bit of visualization. Let us actually visualize the Gudermannian function and its inverse in the Cartesian plane. And here they are side to side. So the first one is the graph of the Gudermannian function, GD of psi, and the second graph is the graph of the inverse Gudermannian function, GD to the minus 1. So here we can actually visualize better how, also graphically, how they are inverses of one another, and how the domain and the ranges of the two functions. In particular, we see that the domain of the Gudermannian function is all the real numbers, while its image is the interval minus pi halves to pi halves. And in fact, we notice that the limit as psi goes to infinity of the Gudermannian of psi is equal to pi halves, and the limit as psi goes to minus infinity of the Gudermannian is equal to minus pi halves. And as we should expect, here graphically we can check too that for the inverse Gudermannian, its domain is the open stripe minus pi halves to pi halves, and its image is all the real numbers, so it's all the real numbers. Here it's something like this. And here now, obviously, we have this. So with this said, there is still more to cover about the Gudermannian function, but for this video I think it is enough. And for the rest, I'll just leave some resources in the links below and some PDFs and documents to learn more about this function. With this said, I thank all of the viewers for the attention, and I salute all of you.